Vertical circles. Hey, Ferris wheels. Ferris wheels. For my ESL students, I did download a picture of a Ferris wheel because sometimes they've never seen the word before. So when we're talking about a Ferris wheel, here is what we're talking about, a wonderful amusement park ride. If you're bored sometime, look up the history of the Ferris wheel. The first one that was built for I think it was the Chicago World's Fair. It was incredible. It was huge. It was still one of the largest ever built. It was only beaten recently. Built by George Ferris, hence the name Ferris wheel. I'll go on an amusement park rant later on. For now, a person rides on a Ferris wheel. Ferris wheel moves in a circle. And what you notice in a Ferris wheel is because the seats are on a hinge, your head always points up, no matter where you are in the circle. Keep that in mind. They sit on a Newton scale that measures normal force. So scales measure normal force so that we don't have to convert it back to kilograms all the time. Emily, we're just going to pretend that this scale measures in newtons. At the bottom of the Ferris wheel, what does the scale read? And convince me. A, the scale reads mg, like it does when you're standing still. B, the scale reads more than mg. Or C, the scale reads less than mg. This looks like a job for a good free body diagram. What are the forces acting on this person at the bottom of the Ferris wheel? Get the obvious one. What else? Acceleration inwards is not going to appear on my free body diagram. I know FC is going to appear in my equation, but it's not going to appear in my free body diagram. There is some, what? Normal force. Now, here is the key. Ready? What path is this person tracing out? What shape? A circle. Where must my net winning force be pointing towards if I'm moving in a circle? The center. Well, that means normal force must be bigger and must be the winner. See how I reasoned that? I said, look, I know I'm moving in a circle. Winner has to be towards, and this is where what you mentioned, Brett, comes into play. I know I'm accelerating towards the center. That doesn't actually show up in my free body diagram. The individual forces do. However, who's winning? My equation is going to look like this. Normal force, who's losing? Minus gravity. That equals the force that's pushing you in a circle. Let's get the normal force by itself. How? Plus the mg over the other side. And now we can answer the question. Right now, all of you are feeling a normal force of exactly mg. That's what you all feel right now. If you're on a Ferris wheel, you're feeling your normal force plus whatever circular force is whatever the centripetal force is. So, are you feeling a lighter or a heavier normal force? Why? You're adding something to what normally it's just plain old mg, and you're adding something to it. You know what? I think at the bottom of the Ferris wheel, you feel heavier, and you do. Now, Ferris wheels move so slowly, it's not all that noticeable. Remember, we said that this here is mv squared over r. And if your v is very slow, you won't notice it that much, unless you really, really think about it and try and feel it. Okay? It says explain your answer using physics principles. I think we just did. I would do a free body diagram and I explain it that way. In fact, example 2 says, on a Ferris wheel, people feel light at the top and heavy on the bottom. Why does this happen? So we've already convinced you why you feel heavy at the bottom. Let's look at the top. What are the forces acting on this person at the top? Get the obvious ones. Why is smaller Fn? Because my net force has to be a winner towards the center because we're moving in a circle. So I know that Fn is loser this time. In fact, my equation is going to look like this. winner minus loser equals FC. In fact, if I get the normal force by itself, what you think of as weight, remember I've gone on a big rant that what you guys think of as gravity as your weight is actually the normal force, right? Let's get the normal force by itself, plus it over, minus that. I think you get this. And again, that's what you normally feel, mg. I guess at the top, you'll feel a little bit less. What you normally feel minus mv squared over r. Again, if your roller coaster is moving very, very slowly, you're not going to feel like you're going to fly out of your seat. But the new one at Playland moves a little faster. They replaced it about 3 or 4 years ago. The old one went really, really slow. The new one goes a little faster. You can slightly feel it, slightly. Says as my explanation, I left you room here, but there's my explanation right there, right? Normal force is gravity minus something. Oh, you got a smaller normal force than gravity. In the previous example, the Ferris wheel is a rigid wheel. The top and the bottom of the wheel will always have the same speed, and the circular motion is uniform, which is nice. But that's not always true for vertical circles. Consider a vertical pendulum like this. I don't know if you can see, but I can certainly feel it. On the way up, because this is fighting gravity, it's slowing down. As soon as it gets over the top, because now gravity is pulling it down, it starts speeding up. And so you have inconsistent speeds. This is actually a surprisingly difficult situation to analyze because it's no longer uniform circular motion. In fact, Graydon, we're going to look at two situations. Here and here. We're not going to look at it when it's here or here or here. The math gets yucky. You can, it's yucky. So example 3, it says write force equations for the vertical pendulum, A at the top and B at the bottom. Let's do the top first. Let's do a free body diagram there at the top. What are the forces acting on that pendulum? Get the obvious ones. Gravity. What else? Is there a normal force? No, you're not sitting on a surface. Is there a rope? What else? Which way? Who's winning? It's a trick question. They both are, right? And I'm not sure which one's bigger, so I'm not quite sure. I wouldn't be too fussy whether you do gravity or whether you drew tension longer. I'll try and maybe figure out later which one's bigger and which one's smaller, and I can go and adjust my free body diagram. Kevin, I can tell you this, though. My equation is going to look like this. Winner plus winner equals FC. What about at the bottom? Okay. Oh, I can actually, you know what? We could even go further. We can say that tension, let's get tension by itself, equals FC minus mg. And you saw when I was spinning, it went slower at the top and faster at the bottom. So we would say this, tension equals mv1 squared over r minus mg. That's at the top. What about at the bottom? What are the forces acting on the bottom? Get the obvious one. Gravity. What else? Sorry? What else? This can't be it, otherwise it can't be moving in a circle. I heard it. What? Bigger or smaller than mg? Here I can say for sure, I think tension has to be the winner. Why? What path are we tracing out? A circle. Where must my net force be pointing? Toward the... So I know tension here has to be the winner. So my equation is going to be winner minus loser equals mv2 squared over r. In fact, if I get the tension by itself, look at those two expressions for tension. Which one is bigger? Sebastian, convince me. It's obvious, so just give me, why? What did you see? Yeah, okay. We watched the Mythbusters video on Wednesday. Tori's swing broke. Where did the swing break? What location was Tori on the swing when it broke? At the bottom. Of course, if it's going to break anywhere, if a rope is going to break anywhere, it's going to be at the bottom of the swing. Why? That's when your tension is the greatest. In fact, if I could spin it really, really fast, I might be able to get this V here so big, I might be able to get this V2 so big that I can snap the rope. That's what happened. Oh, let's look at this one here at the very, very top. I can actually set this up so that at the top for a split second, tension is 0. Watch. Slow down, slow down. You see slack in the rope there for a split second? Yes? That's probably a little bit too much. But I can actually achieve an equilibrium point. I can get tension to be 0. If tension is 0, what I'm really saying is I've found exactly the right speed so that this equals that. In a vertical circle then, the net force is still inwards, and it's v squared over r, or 4 pi squared, m4 pi squared r over t squared. There can be tangent forces that speed up the object, like gravity does. No horizontal forces. We're going to content ourselves with top and bottom. Roller coasters. Turn the page. This is different from the Ferris wheel. You may remember in the Ferris wheel I said your head always points up. In a roller coaster, your head always points towards the center. Okay, so here we got our roller coaster loop. A 70-kilogram passenger is moving at 10 meters per second at the top of an upside-down roller coaster. Find the force the seat exerts on the person. What's this question really asking me to find? Normal force, because I've never written down force seat ever, right? Normal force. Okay, so find Fn. All right. What are the forces acting on this roller coaster? Get the obvious one. On this person, get the obvious one. What else? Normal force. Which way? Towards the center, right? Towards the center. Now, I'm not sure which one's bigger, but I can tell you I got the direction right. Who's winning? It's a tie. They both are. My equation's going to look like this. Normal force plus mg equals mac. Right? Normal force equals mac minus mg. Which equation for circular acceleration do they want me to use? V squared over r or 4 pi squared r over t squared? And how can you tell? Ah! Nothing? You awake, Jen? Okay. We got that, or we got this. Which one do they want me to use? Yeah, they gave me V. Okay, so my equation is going to look like this. The normal force is going to be mv squared over r minus mg. It's going to be 70 times 10 squared all over, where's the radius? Oh, it's on the diagram. 8 minus 70 times 9.8. (70 times 10 squared divided by 8 minus 70 times 9.8). 189 newtons? By the way, what's the normal force this person feels? Normally they just feel mg. Normally they feel 70 times 9.8. Normally they feel 686 newtons. So at the top of this roller coaster, will they feel lighter or heavier? Lighter. They'll feel like they're about to fall. Ah! Fun, good ride. What would happen to the scale reading, to the normal force, if the coaster moved slower or faster? You know what? I think, before I write that, I think the key is this equation right here. I think if I can say normal force equals mv squared over r minus mg. There's my equation. We're not changing the radius, we're not changing g, we're not changing the mass. What we are changing is v. So what you really want to ask yourself is, as v gets bigger or smaller, what happens? The first thing it says slower, so as v gets smaller, hey, what happens to the normal force? If this number here gets smaller, what happens to what this works out to? Smaller, bigger, or stays the same? I heard someone say bigger, I heard someone say smaller. Convince me. Doesn't it get smaller, I think? If you put a smaller number in there, if you put like a 5 there, wouldn't you get a smaller number here minus that? Get a smaller answer? And in fact, could you not go so slow that this worked out to a smaller, to less than this, and you get a negative answer? What that's really telling you is if you go that slow, you're falling off the track. Okay? So as v decreases, normal force decreases, gets smaller. As v increases, is that okay? Cool. That makes sense. Yeah. Yeah. As this gets bigger, in fact, I could probably go so fast that I could make this twice as big as mg, and then you would feel like you're getting pushed up into your seat. Right? Yeah. Okay. I'm curious, or I like that idea of, hey, what's the minimum safe speed before we start to fall? So 6, if the pendulum in example 3 or the upside down roller coaster of example 5 were moving at the minimum safe speed, what would that imply about the forces? Let's come back to that. You know what? It says, find an expression for the minimum safe speed at the top of a vertical loop. So at the top of a vertical loop, we have tension plus mg equals mv squared over r. We have normal force plus mg equals mv squared over r. It's easier to see what we're getting at with my on a string vertical pendulum here. If I hit the minimum safe speed, what can you see happening in the rope for a split second? Do you see it? That was exaggerating. What did you see in the rope? So what does that mean? What's tension if there's slack? 0. So if I'm exactly in the butter zone, exactly in the right area, I would get tension to exactly 0 and no slack. You get that. You get mg equals mv squared over r. Oh! I noticed something else too. And if I want to get an expression for the speed, if I want to get the v by itself, I think times by r and square root, the minimum safe speed is the square root of g. What about for a roller coaster? Well, I think in the roller coaster, you're at your minimum safe speed not when tension is exactly 0, but when what is exactly 0? When the normal force, when you feel like you're about to fall out, to fly out. And do you notice we get, Vlad, exactly the same expression, mg equals mv squared over r. And again, we would then say, hey, the mass cancels. And we would get the minimum safe speed for a roller coaster is the square root of g. And now we can answer part A. It said, what would that imply about the forces? Tension and normal force are 0. When that happens, Chase, that is minimum speed. Go slower than that, you're in trouble. Here's an experiment that you can try at home if you haven't already at least once in your life. I'm hoping most of you are curious enough that you may have done this at least once in your life. Spinning a bucket of water. This is great to do on a warm day. I used to do this all the time as a kid. And you would try and see how slow you could go, but still keep dry. And worst that happened, you got sloshed a little bit. It's great fun, right? So if we spin a bucket of water fast enough, it is possible to momentarily invert the bucket and yet not have any water fall out. Why? How many of you have done this before at least once? Okay. Did you get wet? The water stayed in the bucket? Why? Witchcraft, magic, why? Let's draw a free body diagram on a drop of water. Is that okay? So here's our drop of water. What are the forces acting on it? Get the obvious one. By the way, you may have noticed when you were doing this, the bucket felt heavier at the bottom and lighter at the top. Just like the roller coaster thing, right? Gravity, mg. What else? I think there's also a normal force. I think the bucket is pushing, just like the chair. Who's winning? It's a tie. Now, as long as this drop of water feels a normal force, it's going to feel like it has mass. It's going to feel like it's still being pressed against the Ferris wheel chair, the roller coaster chair, the bucket. So I'm going to get the normal force by itself. And here's what's happening when you're spinning a bucket like that. As long as mv squared over r, the circular force, is bigger than mg, we stay happy dry. Because as long as mv squared over r is, as long as this term right here is bigger than that term, you have a normal force, a positive normal force, which means that little drop, that molecule of water, feels like it's being pushed up against the bucket. It's an artificial gravity, just like spinning a space station. Oh, I can't control the mass of the water. I can't control the radius of my arm. I mean, I guess I sort of can, but most of the time we do this with arm outstretched. What can I control fairly easily in this equation? Speed. And in fact, you may have done this when you were a kid. The fun part is to see how slow you can get to try and get as close as you can to the equilibrium. And if you go too slow, then you end up with this expression being less than gravity. You get a negative answer. You get wet! Which on a hot summer day is also fun. It's like no-lose physics. It's only winners. It's great. You either get soaked or you learn something. Cool. Wow. Speaking of artificial gravity, let's go to our space station again. We looked at the space station earlier under horizontal circles, but really, Jimmy, I could treat it as a vertical circle too, because there is no up, down, left, right in outer space. It's outer space. So here's a space station. It has an outer radius of 140 meters. The space station rotates so that the occupants at location X experience an acceleration of 9.8 meters per second squared. Emily, they experience artificial gravity. What acceleration will the occupant at location Y experience at the 100-meter radius? I think, if I'm reading this correctly, we're going to use location X to figure out something at location Y. Now, I do notice that they did give me right there the velocity, but I don't think I'm going to use V for this. The reason is, Dylan, I think this person's velocity on the outside is traveling faster than this person's circular velocity on the inside. I don't think they share the same velocity, but I do think they share the same something else. The other equation, important variable. Period. I think they rotate in the same amount of time, but for that to occur, I know they rotate the same amount of time because they're part of the same space station, but for that to occur, this guy's got to be traveling faster than that guy, because he has a longer distance to travel. So I'm not going to use V. I'm going to say, you know what? My plan of attack is to see if I can use location X to figure out the period, transfer that period to location Y, and figure out the acceleration. What are the forces acting at location X? Get the obvious one. Oh, I can't say get the obvious one this time. How come? Outer space. So what are the forces at location X? Just the normal force pushing up. That's the artificial gravity. That's what you all think of as your weight anyways. Right? In fact, my equation in location X is going to be normal force equals what's pushing him in a circle, or her in a circle. And I think we've already said that we want this to be m4 pi squared r over t squared. We've agreed, you know what? It's the period that's the same at both locations, not the velocity. I don't know the normal force. Oh, but look. They've told me what I want the acceleration of the normal force to be exactly. What? And we've seen that 9.8 before. Where have we seen that 9.8 before? I think what they're saying is we want artificial gravity to actually be mg, the normal force to be mg. Oh, cool. What period does this space station need to have? 4 pi squared r over g square rooted. I think the period is going to be the square root of 4 times pi squared. R is 140, is that right? Divided by 9.8. Is that okay? And I get, you know what, I'll carry a few extra sig figs. I get a period of 23.74, how about 23.75? It rotates every 23.75 seconds. If you're on the outside of the space station, you'll feel normal, no pun intended. You'll feel a normal force of mg. In fact, you won't be able to tell, unless you look out the window, that you're not on Earth. If you drop a ball, it'll look just like you dropped a ball on the Earth. What about at location Y? Well, I think at location Y, it's going to be the same free body diagram. This time the acceleration is not g. I'll call it a at 100. Because that's what they're asking us to find. They're saying, hey, if the guy outside at 140 feels 9.8, what does the person at 100 meters feel? But that's still going to be, Joe, m 4 pi squared r over t squared. I still don't think it matters how heavy you are. What will the person feel at 100 meters? They'll feel 4 pi squared times 100 divided by, what was t, 23.75? I'll write 23.75 squared, but I'll use the actual calculator value that I have stored, Austin. 4 pi squared times 100 divided by answer squared. Oh! Works out dead even. .0 meters per second squared. You would still feel an artificial gravity, but it would be slightly lighter. When you dropped something, it would look funny. It'd be feeling like it would look like it was falling just a little bit too slow. Your reaction time would probably be off. Playing catch would be both fun and challenging. Right. You would feel stronger for a while. You'd be able to lift a little bit more than normally. You'd be placed to bench press, but probably in a month or so, over a month or so, your muscles would atrophy unless you went back down to the 140 meter area where it was 9.8 as often as possible. Pardon me?
Wouldn't it be the same?
Would your muscles be working harder? The real issue for low G environments is your heart muscle, because that gets weak very fast. It is used to having to push blood up to your brain. You don't notice it in outer space, but when they come back down to the Earth, they're in bad shape, and they've got to take a lot of time, like especially the ones that do extended stays on the space station. Right, the Canadian guy that's up there right now, he's probably going to have several months of rehab when he gets back down to the Earth, because it's your heart muscle that gets weak. Yep. Example 9. A 75-kilogram person rides a Ferris wheel which is rotating uniformly. The centripetal force acting on the person is 45 newtons. What force does the seat exert on the rider at the top and at the bottom of the ride? What's this question really asking me to find? Normal force, okay. And I'm seeing top and bottom, so you know what, Sebastian, I'll go... Let's do the top first. What are the forces acting at the top? Get the obvious ones. What are the forces acting at the top? Get the obvious ones. We're back on the Earth now.
Gravity.
Darn right. What else? Longer, the same size, or shorter than gravity? And convince me. Okay, what path are we tracing out? A circle. Where must my winning net force be? Toward the, which means I better draw normal force shorter. My equation is going to be winner minus loser equals FC. Compare that with the bottom. What are the forces acting on the person at the bottom? Get the obvious ones. Gravity. What else? Normal force. Longer, shorter, or the same length as gravity? Why longer? So are you saying my equation is going to be winner minus loser equals FC? Almost identical equations, but not quite. Let's get the Fn by itself. It says here, normal force is going to be mg minus Fc. Here, normal force is going to be mg plus Fc. Right? Did they give me the mass? What was the mass? 75 times 9.8 minus, and here they gave me Fc. I think on a test, if I give you this question, I wouldn't actually give you the 45 newtons. I would give you the radius and the period, or the radius and the velocity. But I'd make you either use mv squared over r or m4 pi squared r over t squared. But here they said, hey, it's 45. Okay. Here I'll have normal force equals 75 times 9.8 plus 45. $75 times 9.8 minus 45, 690 newtons at the top. 780 newtons at the bottom. It's your homework. Now, I'm going to circle number 1. Unlike the bucket of water experiment, this one I'm not so sure I encourage you to try at your home, young drivers who are stupid. But I'm going to assume all of you at least once have gone over a hill or a bump and felt your stomach, felt that kind of weightless feeling, okay? This question is asking, all right, if you know the hill is in the shape of a circle, how fast do you have to go to leave the ground? Because that's what apparent weightlessness is. See if you can crunch it out. Number 1. 2 is good. Take a look at number 3, please. Number 3, I'm not going to assign, but if you were wondering, because some of you are curious, hey, Mr. Duick, what would the equations look like for at an angle in a vertical circle instead of just straight at the top and the bottom? You bring in some trig and some components. Meh. 4 is good. 5 is good. 6 is good. 7 is good. So far I've skipped 3. 8 is good. So 8, we're looking at fighter pilots. Fighter pilots do 2 types of loops. They do what's called an inside loop. That's where their head is pointing towards the inside. That's what this question is talking about. They can also do an outside loop where you pull up over the top. That's where your head is always facing on the outside. There, you're much less likely to black out because there, it's going to feel like the blood is getting forced into your brain. In fact, the blood wants to keep going in a straight line. Your brain moves into its way. So there, the danger isn't from blacking out. There, the danger is actually from bursting blood vessels in your eyes or in your face. So you still got to be careful. But here, 8, nice fighter pilot question. You'll have to change things to meters per second, but see if you can figure it out. Number 9, here's a horizontal question review. That's fair game. I'm going to circle number 10 and then put a star next to it. Number 10 is, I'm not going to ask you this on your test, but I'm going to see if you want to try, especially those that are really into this, try figuring this out. Also because you're getting your driver's licenses, you should know the physics of banked corners. So see if you can figure out how to do a banked corner, what your force diagram would look like. I'll give you a hint. That's it. No friction. and see if you can get the equations for part B, and see if you can actually find what angle theta is required. If you can't, that's fine. Same with number 11. I'm going to circle it, putting a star next to it. I'm not going to assess you on it, but it's good discussion. I don't mind talking about it and see if you can figure it out. And number 12 is fair game. Seems like a lot. You're going to get a full half hour, but I got a couple of movies to show you first. Little video.